Hello everyone, my name is Roy Halley. I'm Head of Product Marketing at EOP Europe. And today I would like to talk about challenges and solutions of accurate power measurement of SiC and GaN based applications. Nowadays, product designers are using more SiC and GaN semiconductors. But why? What makes them so interesting? And what is required to accurately measure the loss and efficiency of SiC and GaN based applications? Let's have a look. To explain this, I would like to take the ongoing development of EVs as an example. The hardware in EVs is constantly under development. Downsizing the powertrain is a good example. As you can see in the center picture, EV car makers and their tier 1 suppliers integrate different parts like the inverter, the motor and the reducer in compact and lightweight assemblies that can easily be installed in EVs. One of the larger and more heavy parts in the inverter is the step-up reactor. To be able to handle the power needed for the EV drivetrain, it has a considerable size. The power that the step-up reactor can handle equals omega L, where omega represents the rotation frequency and L the inductance. So to reduce the size and weight of the inductance L, it is required to increase rotation frequency omega. This can be done by increasing the switching frequency of the semiconductors in the inverter. SiC and GaN semiconductors can operate at higher switching frequencies and have less switching loss than silicon semiconductors. All this together makes it possible to design smaller, lighter, and more efficient inverters with SiC and GaN semiconductors. Downsizing also gives engineers more freedom in their designs and reduces the use of popular raw materials, like in this case, copper. In a nutshell, this explains the popularity of SiC and GaN semiconductors. The use of SiC and GaN semiconductors creates, however, some measurement issues. It is much harder to measure accurately at high frequencies and at low power factors. Let me explain you why. The first challenge that we face is the influence of the phase error. I like to explain that with the two phase diagrams on this slide. On the left side, you see the vector diagram of a high power factor device like a power resistor. In this case, the influence of the red phase error is small in comparison to the active power. However, when we look at the right side, we see that measuring the low power factor device, like a step-up reactor, the power error has much more influence on the measured active power. This shows that it is extremely important to compensate the phase error, especially when you want to measure the loss of low power factor devices at high frequencies. How can we achieve this? All measuring systems are affected by phase error. The equation for real power is shown here. To be able to measure power accurately, it's necessary to accurately measure the voltage, the current, and the phase and the power factor. Generally speaking, the voltage measurement is quite simple. For the current measurement, it's different, however. All the different current measurement methods create phase errors. Internal shunt resistors, for instance, have a low resistance and are by nature inductive, which makes them unattractive for high-frequency measurements. EOP is predominantly using external current sensors with a voltage output. This type of current sensor will cause a phase error, as you can see in this frequency diagram. The red curve shows that there is a noticeable phase error at frequencies higher than 10 kHz, your conclusion probably is that this current sensor is not suitable for high-frequency power measurement. But that is not the case. Let me explain you why. The design of the Hioki current sensors guarantee a constant frequency response. In other words, all sensors with the same model code will have identical frequency characteristics. This unique feature makes it possible to develop the automatic phase shift correction function. The latest generation of Hioki current sensors have an internal memory which contains the model code, current range, phase error information, and serial number of the sensor. When the current sensor is connected to the new PW8001 power analyzer, it will be recognized automatically and all the relevant information will be registered in the PW8001. Here you see two screenshots where it's clear that the CT6846A current sensor has been connected to channel 8 and that the phase shift correction data is automatically set to compensate for the phase error over the full frequency band of the measurement. In other words, you don't have to worry about phase errors anymore. We call this automatic phase shift correction, APSC, and it is a plug-and-play solution unique for the market today. The second challenge that the frequency increase has created is the influence of high-frequency switching noise. To explain this phenomena, I like to go back to the reactor loss measurement. On this slide, we see a typical circuit for reactor loss measurements. In the center graph, you see at the top U1, the 100 kHz square-shaped test voltage. Due to the hard switching of the semiconductor, EMC noise is generated at 100 kHz and its harmonics. If we take a look at trace I2, it becomes clear that this current sensor is not suitable for accurate loss measurements. The yellow trace E1, however, shows a current signal that is not affected by the high frequency switching noise. Reason for this is the high common mode voltage rejection ratio of 120 dB at 1 MHz. The 120 dB is equal to only 1 ppm interference of switching noise at a frequency of 1 MHz. This example shows that it's not enough to use a power analyzer with a high common mode voltage rejection ratio. The current sensor that you use should also have an excellent common mode rejection ratio. We have seen some challenges and solutions of today's power measurements. Now, let me introduce some features of the technology behind that. Hioki's new flagship power analyzer, the PW8001. The PW8001 has a 10.1 touchscreen and can handle up to 8 power channels. There are two types of input units that can freely be combined. The high accuracy unit U7005 and the high voltage unit U7001. The basic power accuracy at 50 to 60 Hz is 0.03% and 0.05% for DC measurements. The highest sampling frequency, 15 megasamples per second, and the day A to D conversion has a resolution of 18 bits. This combined makes it possible to view high frequency PWM voltage waveforms in detail on the screen of the instrument. It can also measure up to 1500 volt DC in a Cat2 environment, complying with the latest IEC 61010-1 edition 3.1 standard that becomes effective on the 1st of January 2022. In combination with the latest generation current sensors, it has automatic phase shift correction function, APSC. This unique feature reduces the setup time and eliminates chances of phase errors, regardless of the frequency and power factor that you are measuring on. It has already been mentioned. Current sensors are an essential part of accurate power measurement. Together with the PW8001, Hioki introduces a range of new current sensors. Here you see the overview of the Hioki pass-through current sensors. This type of current sensor provides the highest accuracy and bandwidth. For instance, check out the new CT6872 and CT6873 with their extremely high accuracy and bandwidth. These current sensors are designed for SiC and GaN applications where switching frequencies can be 100 kHz or higher. It is our mission to provide true power analysis for engineers in pursuit of the highest power conversion efficiency. The PW8001 power analyzer and the new current sensors provide a highly accurate solution perfect for SiC and GaN applications or multi-channel power measurements. The series will be released in the middle of December 2021. Thank you very much for your attention. Bye-bye.